Okay, hello everyone. Welcome to the problem solving sessions for Introduction to Automata Languages and Computation. So there was a technical error at my end, because of which the recording did not. Only the audio got recorded. So I'm doing a re-recording of the tutorial. Okay, so okay, so so let's talk about briefly about what are the topics that we're going to look into today. So last time we saw what are called context-free grammars, and so this week what we saw what is called ambiguity. So when do we say that a grammar is ambiguous? So this time what we'll do is we will see um, yeah we will see how to, if a grammar is ambiguous, then how to make it unambiguous. So and we will look into two special kinds of grammars. One is what is called Chomsky Normal Form, which is CNF, and the other is what is called GNF, or Greybach Normal Form. Okay, so we will talk about the definitions whenever we look at the example of certain kind. So just want to give an agenda of what we're going to do. So let's start with some warm-up questions. Okay, so here you are given a grammar which is given by these productions. So what are the set of terminals here? The terminals are a, b, and epsilon. And what are the variables here? Or the non-terminals? The non-terminals, yeah, the non-terminals are capital A, capital B, and capital S. And S is the start set, and these are the set of production. So these all together they define grammar. So what this question asks you is that you are given four different kinds of grammars here, which is A, B, C, D, and you want to tell which of these are equivalent to the given grammar. So when do we say that two grammars are equivalent? So let's write that. So it's very similar to the case of DFS. When you say that two DFS, M1 and M2, are equivalent if the language that they recognize is the same. So in this case you say that two grammars G1, G2 are equivalent if the language of G1 is equal to the language of G2. So that is when you say that they are equivalent. So in order to solve this problem, what we will do is, for each of the grammars we will try to identify what is the language that they recognize. So let's start with the first one. So I'll try to get a new page here. So here you have you have S gives AB, A gives AA or epsilon, and B gives BB or epsilon. So this is the grammar, this is exactly the grammar that we had, and I'm just writing it here. So what we want to do is we want to tell what is the language of this. So you have if you start with when you start with this, there is only one production, so S gives AB. Now if you look at A, it has two productions. It can give A, non-terminal A, preceded by a terminal A or epsilon. So let's say it gives you AA, and this can happen several times, and ultimately this A will terminate in epsilon. Similarly, if we look at capital B, then this can give you B several times, and ultimately it will terminate in epsilon. So what is the language that is generated by the grammar? So on this side, from the left side of the tree, you would have derived several number of a's. How many a's can be there? There can be a star, there can be uh, any uh, n greater than equal to 0 many a's. So hence you have a star, because here a can terminate in epsilon. So here itself at the beginning a could have given epsilon, so it can also generate epsilon. Then with the same argument, exactly same argument, you can say that on the right hand side you can generate any number of b's. So your grammar is going to, the language of this grammar is nothing but a star b star. Now let's see, let's look at each of these options. So let's take a, let's look at this grammar. So you have so you have s gives as or b, and b gives bb or epsilon. Okay, so let's look at the language of this grammar. So at the beginning you have s, and let's say s gives you as, and this can happen several times, and ultimately s will have to terminate in b after several steps. Then b can give you couple of b's, and this can happen several times. Ultimately b will terminate in epsilon. So what are the strings that you are generating here? On this side you are generating some number of a's. Note that the number of a's can be 0, because it is possible to produce epsilon. From s you go to b, and from b you go to epsilon, or from b you can take as many b's as you want, and then finally terminate at epsilon. So so it is possible to have 0 a's and just no a's but just b's, so that is possible. Hence this has to be a star. And with the same argument you can say that here the number of b's that are produced after that is b star, because from b you could have just directly taken epsilon. So the language of this grammar, let's call this g1, this is a star b star. Okay, so then we have that L of g is equal to L of g1, because earlier we saw that the language of this grammar is also a star b star. So hence you have that the grammar that is given is equivalent to the grammar of option A. So hence you have that A is definitely equivalent to the grammar that is given. But that does not mean that that none of these can be equivalent, because we know that for the same language it is possible to have different grammars. So it is possible that one of the remaining options is also equivalent. So we will have to check through each of them and see whether the language is the same. So that's what we will do. Let's look at the second one. So here you have s gives a as b or a. And a gives a or epsilon. So let's look at the language of this. So you start with s, and let's say s gives a as b, and then this happens, let's say, several times, a as b. Ultimately at some point s will have to terminate in a, and then a can give you several a's here, and ultimately it will terminate in epsilon. So what is the language of this? So you can think of this in terms of two blocks. So let's say this is the first block that is generated, this is the second block that is generated, and this is the third block that is generated. So notice that the any string of this is going to be a star, which comes from b1. Then you are going to have a bunch of, let me call it a to the k. Then you can have some l many zeros which comes from this b2 block, and then you can have some number of b's which come from the b3 block. But notice that if you have k number of a's here, then you will have exactly k number of a's here, because for every a that is generated there is a b that comes up. This happens as many times as you use this ASP production. So the number of b's here will have to be equal to k. And what can we say about k and l? So k can be 0, because from s, instead of going to any ASB, I can directly go to a, and then a will have a production of its own. So it is possible that I don't use ASB at all. So yeah, so therefore k can be 0, so k is greater than equal to 0. And similarly for l, l comes from l comes from this block, and without ever using this a production, if I directly say that a gives epsilon, then we would not have generated any extra a's. So l can also be 0 because of the epsilon. So here you have l greater than equal to 0. So the language of this grammar is nothing but a to the k plus l followed by b to the k, where lk is greater than equal to 0. And notice that it is, yeah, it is okay. So the question is the language of G2 the same as the language of G? That is the question. So yeah, so observe that this language cannot generate strings that are of the form. So let me take an example. So let's say you have a followed by b. So this string is in the form a star b star, so hence a b, this is in the language of G. But can a b be in the language of G2? That is the question. So since the language of this is a to the k plus l followed by b to the k, the number of a's cannot be less than number of b's. So hence this string would not be in the language. So here you have one string a b, which is in the original grammar G, but it cannot be generated by the grammar G2. So these two languages are not equal. So therefore we conclude that L of G is not equal to L of G2. Therefore G2 is not equivalent to G. So B is not the correct answer. So similarly we will do similar checks for part C and part D. So yeah, let me write this grammar on the other page. So or okay, so I've just copied this grammar on the other page. Now we are going to do same thing. We will identify, our goal is to see what is the language generated by this grammar. So you are at S, and let's say you apply this first production. So what you get is, you get ASB, then you have ASB, and this will happen couple of times. Ultimately if you use A, then A will generate several A's like this, and ultimately it will terminate in A. So in this case, the language would be A to the K, A to the P, followed by B to the K, where K is greater than equal to 0, because it is possible that I don't use this ASB at all and I directly use A, or I directly use B. So that is possible, hence K can be greater than equal to 0. But what can we say about P? In this case, A has two productions. So one is A gives the terminal A followed by the non-terminal A, or it gives you simply the terminal A. So it doesn't give you epsilon, hence P cannot be 0. So P has to be at least 1, because of this condition that A gives a terminal A. If instead of small a, if it had been epsilon, then then you can say that P is greater than equal to 0. So similarly, if you use the B transition here instead of using A, then you would end up getting some strings of the form b to the p, b to the k, where k is greater than equal to 0. This follows from the same argument, and p is greater than equal to 1. So what that means is epsilon, the string, so just to make sure that we don't confuse the epsilon string with the membership symbol, I'll write epsilon as yeah. So notice that the string epsilon is contained in the language L of G, because epsilon is of the form a star b star. Okay, so this is there. But what can we say about epsilon? Epsilon's membership in the language G3. So I'm calling this grammar G3. Okay, what can we say about this? Note that whether you take A or B, you will have to terminate in small a, or you will have to terminate in small b. So you cannot generate the empty string at all. So this string is not in the language of G3. So hence you have that L of G is not equal to L of G3, and therefore since the languages are not equal, you have that the grammars are not equivalent. So therefore G is not equivalent to G3. So similarly, let's do the final example. So final example is okay, I'll get a new page. So D part says that this is your G4, S gives A as B or epsilon, and A gives A or epsilon, and B gives BB or epsilon. So this is the so this is the grammar that you have. And what we will do is we will try to find the language of this. So if you are at start symbol S, then you can basically do A as B, and this can happen several number of times. But what does A do? A gives you bunch of A's. This A would give you bunch of A's, and similarly B can give you B star, and this B can give you B star. That is from the same arguments that we've been seeing earlier. So that just follows from the two productions that we have. Now this S is finally going to terminate in epsilon. So what are the strings that you get? You get strings of the form A star, A star, A star, followed by A star some k times, followed by B star some k times, and okay, actually this is so this is A star, A star, A star, followed by B star, B star, B star, and and this is nothing but A star, and this is nothing but B star. This follows from the properties of clean closure. So this is something we have seen earlier when we saw the regular languages. So I'm just using the property here. So hence the language of this grammar, which is G4, is nothing but A star, B star, and this is equal to the language of the original grammar that we had. And because of this, we have that G is equivalent to the grammar G4. Hence the final answers that we have is, we already saw that A is equivalent to the grammar that we have, and D is also equivalent. So A and D, that is the answer. So I hope that is clear. So basically the takeaway is that if you want to see whether two grammars are equivalent, then you look at the languages that they generate, and check whether they are equal. So that's the thing. Now if that is clear, let us do some examples of you are given a language and you want to tell what you want to generate a grammar for it. So let's do it one by one. So let's do part A first. So let me just define what is the language, so that it is clear. So what is the language? So here you have, let's say L1 is the set of all W followed by X, such that X reversal is a substring of X. So notice that we've seen reversals like so many times, right, so far. So what do we mean by reversal? So if I give you a string which is apple, and let's say this is X, then the reversal of this would be just reading the string from right to left. So that would be ELPPA. That is the reversal. Just that you, instead of reading the string from left to right, you're going to read it from from right to left. That is the meaning. Now, what do we mean by X reversal? Is a, sorry, I think this should have been W reversal. Yeah. So this is W reversal. So what do we mean by W reversal being a substring of X? Suppose W is 0 0 1 1 1 and X is 0 1 1 0 1 1 1 0 0 1. So let's say this is X and this is W. So what does W sharp X look like? This is 0 0 1 1 1 sharp 0 1 1 0 1 1 1 0 0 1. So yeah, so what I mean is, if you look at this X, then there is a substring. Okay, so let me write W reversal explicitly. W reversal would be just reading this string from right to left. So this is 1 1 1 0 0. So do you see a 1 1 1 0 0 here? It is 1 1 1 0 0 is indeed a substring of X. So yeah, so this thing would be in the language L1. But if I modify X, so W is the same, W is 0 0 1 1 1, but if I say X is 0 0 0 1 1 0, 1 1 1 0, then W sharp X is not in the language of L2, because no matter what substring you look at, this reversal 111000 is not contained, is not a substring of X. So this thing would not be in the language. So if that basically we are saying that you look at the first part W, look at its reversal. Is it present in the second part? Is the reversal present in the second part? Somewhere in between, that is the question. So yeah, so if the language, that is the that is what I wanted to say about the language. If that is clear, can you try to come up with a context free grammar for it? So I'll wait for some time, so that you can attempt it, and we will discuss this in 1 minute. Okay, so let's discuss this. Okay, so let's basically we want to write a grammar for L1, but what we will do is we will build this in parts. So just to simplify, I'll simplify the language, and let's try to make a grammar for it first. So let's say L prime is the following language. It is W followed by W reversal. Okay, suppose I want to write a grammar for this. What will I do? So simplest idea is that you write S, give 0 S 0 or 1 S 1, and end it in sharp. So what this says is you are at the starting variable S, and if you generate a 0, I want to generate a 0 at the end. So if you are reading the symbol here, I want this symbol to be exactly equal to the symbol at the end. So if this is 0, this should be 0. This is 1, then this better be 1, and so on. So this is the idea. So that's why it makes sense to write 0 as 0. Similarly, if you have if you want a 1 here, the second symbol is 1, then you want to write a 1 at the end also, so that the string is exactly the same from the reversal. So This can go on for a while, and finally you want to mark the end of the first string with the sharp. That is because there is a separator between the two strings, so hence you end with a sharp. That's the whole idea. So this is the grammar. Yeah, so this is the grammar for the language L1. Now um, yeah, now let's look at the language that we want. The language that we want is L1, which is of the form W sharp X W reversal Y, where W, X, Y are strings in 0 1 star. So what do we mean by this? We are saying that if you look at this, so I maybe I'll use a different notation. I'll call this Y and Z so that there's no confusion. Right. So if you look at this string W sharp X, then we are saying that it should contain W reversal somewhere. So let's say it contains W reversal here. There could be something before it and there could be something after it. So let's say that the string before it is X and the string before it is Y and the string after it is Z. then then this is exactly what we want to generate. Y can be something, can be some string over 0 1, and Z can be some string over 0 1. So this is what you have, and we want to generate the grammar for this. So we will do this in parts again. I'm going to modify this slightly. So um, yeah, so let's look at this. um, yeah, so what I'll do is, instead of writing a sharp here, I'm going to change it slightly. So what I'll do is I'll make it S gives 0 as 0 or 1 as 1, or sharp B, where what does B do? B gives you any string over 0 and 1, 1B or epsilon. So now what is the language of this? What is the language of this? So S gives you 0 as 0, it gives you, let's say, 1 as 1. So you would have generated some string here, some string here, and this is, if this is W, this is W reversal. Ultimately this S is going to give us sharp B. And what does B do? B gives us some string over 0B, 1B or something. So this is some string Y over 0 1. So what is the language here? What are the strings generated here? It is W sharp Y followed by W reversal, where Y is a string in 0 1 star. So just by modifying this, so this is the only modification we made. We added a new non-terminal B, and B is this production. B basically generates any string. So just by doing this, what we have done is we wanted to generate strings of this form, W sharp Y W reversal Z. What we've done is we are now generating W sharp Y W reversal. So we are almost there, just that only thing we need to make sure is that we need to add Z's here now. So we want to generate Z's after the reversal. So that means since W reversal is somewhere here, there should be something over here that takes care of the Z. So that is intuitively what should happen. So we'll do a small modification now. So I'll call this, yeah, I'll say as I'm modifying the start symbol. So let's say A is the start symbol now. So A gives S followed by B, and yeah, and S gives 0 as 0 or 1 as 1 or sharp B, and B gives 0B or 1B or epsilon, and that's it. So this is the final grammar that you have. And why does this work? This works because it's just that you have a new start variable here. It will give you S followed by B, and B will basically generate some string Z over 0 1, and the rest of the things remain the same. So that basically takes care of the extra Z part. So this is the final grammar for part E. Okay, so if that is clear, so yeah, what did we do? We basically broke this into smaller parts. Instead of looking at text in general, we looked at just a small case where you have W followed by W reversal. Once that is done, we took care of a small fragment which was some string before W reversal. So adding this helped there, and then you just had to take care of the preceding strings, sorry, the following strings. So this small modification by changing the start set is what we did, and that basically takes care of the grammar. So now, if that is clear, what I want, so the second example is somewhat in similar spirit, but it is somewhat challenging to come up with. So I would really like you to try this out once before we look at the solution. So so if you're watching the video, then please feel free to pause it and give it a try once before we discuss the solution. So so I'll maybe wait for a minute and okay, maybe let me just explain what this grammar is. Okay, so the language, let me call this language L2. L2 is set of strings such that all of the xi's are strings over 0 1 star, and there exist I comma j such that xi is reversal of xj. So what we mean by this is that there are bunch of strings here. So x1, then there is a separator, then there is a string x2, then there is a separator, and so on. And what we are saying is that there are going to be two indexes, some xi here and some xj, let's say here, such that if you look at these blocks, then xi is nothing but xj's reversal. This is something we saw earlier, but additionally it can have some it may have some blocks of strings before it may have some blocks of strings in between, and it may have some blocks of strings after it. So all these possibilities can happen. So you want to, okay, maybe just take an example. So as an example, let's say 0 0 0 followed by, okay, so let's say this is x1, this is x2, this is x3, and this is x4, this is x5. Let's say this is the string that we are given. So note, so observe that here if we look at x2 and we look at x4, then x4 is nothing but the reversal of the string x2. So yeah so that is what we have, and therefore this is going to be in the language L2. But if I say that this is the strings that you have 0 1, then you have 0 0, then you have 1 1 1, then there does not exist any two blocks here such that one is the reversal of the other. So this is not going to be in the language L2. So that's a basic thing. So you have lots of strings which are separated by the hash symbol, and a string is going to be in the language if there exists two blocks such that they are reversals of each other. So so that is basically the idea. Now I would like you to think about this and use the ideas that we saw in the part A to come up with the context free grammar for this. So I'll maybe wait for a minute, or you can pause the video and think about it, and I'll discuss this in some time. Okay, so let's look at the solution. Okay, so like earlier, we will approach it in the similar fashion. We will try to simplify the problem, get a grammar for the simple problem. Then we will add more constraints to obtain the final grammar that we for the language that we wanted. But we will do it in parts. So yeah, so we will do it in parts. So what we will do is, let's say I want to get a grammar, so my language L2 prime is as follows. You have a bunch of blocks x1, x2, and so on up to xk, such that x1 is reversal of xk, and you have that x2. Okay, so I've simplified the problem in the sense that I'm saying that the reversals do not occur somewhere in between, but the reversal are the strings at the tail ends. So if that is what we wanted to do, then yeah, let's say you have a start symbol that yeah um, that kind of gives you 0 s 0, 1 s 1, and so on. So this is basically generating the string x1 for s, and this is basically generating the string xk for s, so that x1 is nothing but xk's reversal. Now what we want to do further is that in between we want to have this sharp x2 and so on sharp xk. We just want to make sure that there is a block of um, yeah, there is a block of strings here that can be generated. So I'll just write whatever we have. We have 0 s 0 or 1 s 1, or you can have sharp followed by there is a block of there's a block of strings that could be there, or it is possible that there is no string in between. It could just be that it is x1 followed by x2, and such that x1 is reversal of x2. So it is possible that there are no blocks in between. So in that case you will just end up with a sharp. So this is to take care of that. Now yeah, so now let us define what this block will look like. So block is going to be, it's going to generate some string with, let's say, c, followed by, there could be more of those, and finally this will terminate in c. So c is nothing but it is capable of generating any string, so it is 0c or 1c or epsilon. So now by the end of this grammar basically generates all the strings of this form. So this is the grammar. If I call this g prime, then g prime is the language of g prime is nothing but L2 prime, because uh yeah, because like we said earlier, so if you do 0 s 0 or 1 s 1, then you get a string x1 here, you get its reversal xk here. If you go with sharp b sharp, then you will have sharp followed by a b followed by a sharp. And what does b do? This b is going to generate all the blocks in between. So this c followed by more blocks and more blocks and as many blocks as we want. So yeah, so that is basically the grammar for L2 prime. Now yeah, now we are kind of building towards what we wanted. Only thing that we did not take care of is that there could be some let's say some blocks here, x0 followed by x1 followed by x2 and so on up to xk, and then there could be some blocks here. Yeah, there could be some blocks here and there could be some blocks here, sorry, some blocks here. So we just want to take care of that, and we know what is the variable that takes care of this for us. It is b is capable of generating all the blocks. So we will do the same thing. So let me get the current grammar on the other page. I'll just get this g prime on the other page. Okay. Okay, so now what we are saying is that, uh, yeah, is that, let's say a is the start variable. Now there could be some blocks before we get to s, and there could be some blocks before we get to after reading s. So this is basically taking care of the strings before and the strings after. Okay, so okay, maybe I'll do it slightly differently. Okay, so this is the grammar that we had, and because it's a start symbol that I'm introducing, I'll just write it over here. So a gives b followed by s followed by b. But it is possible that there is no block, so there is x1 to xk such that x1 is the reversal of xk. It is possible that there are blocks after it, but there need not be blocks here. So it is possible that there is nothing here. In that case, I don't want to use this extra sharp because that is not how the string starts. So what we will do is, in that case, you just have s sharp b. Similarly, you can argue that it is possible that maybe there is a bunch of strings here, which is what I'll get from b. Then you have xk, but maybe there is nothing here, maybe this is where it ends. So in that case, I don't want this redundant sharp b. So symmetrically, you can say that it is possible that it is b sharp s. And then you can argue the same for both the sides. You can say, okay, why should there be strings here and why should there be strings here? It is possible that it's just x1, x2 and so on up to xk, and we know that s basically generates it, so a can directly go to s. That is what s anyway generated. So just adding this one more transition here is kind of taking care of all the constraints that we had. So this now addresses all the constraints, and we are exactly capturing the language L. So this grammar here, if I call this G, then L of G is equal to L2 that we wanted. So yeah, so that is the grammar for the language that we wanted. And just to recall, what we did was, like earlier, we kind of broke this into smaller and smaller, easier and easier languages. So first we looked at this language, where instead of arbitrary blocks in between that are reversals, you have that the left one and the right one, those are the reversals of each other. Then we wrote a grammar for this. Then we added just one more constraint, that it is possible that there could be blocks before it and there could be blocks after it. So these four conditions, the four productions that we have, take care of all the exhaustive cases that can be there. So ultimately, the language of this grammar is nothing but the language that we wanted to generate. So yeah, I think you can formally prove this also. This is a very hand waving statement that we did. It is possible to formally prove it. It takes somewhat efforts to mathematically write this, but I think it is a good exercise to try. So if you I would encourage you to try to prove this. Okay, so if that is clear, okay, I think I'll take up this example maybe next time. So right now what I want to talk about is what is called a CNF. So okay, sorry. So let me get a new page. So let me recall what is a CNF. This is called Chomsky Normal Form. So what do we mean by this? So generally, when you are given a grammar, you are given the set of four tuples, you have the set of you have the start variable, you have set of variables, then you have set of productions, and then you have a set of terminals. So this is this using this 4 tuple you can uniquely define a grammar. Now what does a Chomsky normal form do? It is going to look at these productions, it is going to give you a new set of productions. So you will modify the variables and terminals appropriately, but you want this productions to be of a certain form. And what is the form? If you are reading a non-terminal, then it can give you either so it can give you either a terminal, or it can give you a product of two non-terminals. These are the only two possibilities that can be there. Anything other than this is not allowed in the Chomsky normal form. So for example, let me take this. So if I give you that um, A gives B C D, this is not allowed because it is a product of more than two non-terminals. If I tell you that A gives A, B, 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 this is also not allowed because it gives you a product of more than one terminals. Similarly, you are not allowed to have something like A, B, C, or you are not allowed to have A, B, because here you have product of one terminal and one non-terminal. So none of this is allowed in the Chomsky normal form. So um, yeah so um, okay, I'll talk more about this when we see more examples, but I think as a simple exercise, just to get familiar with this, maybe you can try out this example. Okay, so maybe sorry yeah so maybe you can try out this example. So yeah, here you have okay, let me use this yeah, so here this is the set of productions that you have. And so capital X, capital Y, and capital S, these are the set of variables here, and the set of terminals is small x, small y, and small z. Now the question is that is this in the first question is this in CNF form already? So if you look at S gives xy small x, then um, yeah, then this is not in the form because you have product of two non-terminals, and that is fine, but you have a terminal at the end, so this is not allowed. So this is not in the Chomsky normal form. If you look at x gives small x followed by small y, then this is also not in the Chomsky normal form because this is a product of um, three terminals, and it only allows you to give something like this or something like this. There's only one terminal that is allowed, so this is also not in the form. And if you look at the last production, it is capital X small z, so you have a product of a terminal and a non-terminal, so this is also not allowed. So none of the rules here is in the Chomsky normal form, so we will have to bring it in the form. So notice that it is possible from every grammar you can go to the Chomsky normal form, and similarly from every Chomsky normal form you can go to the GNF, which is the Greibach normal form. We haven't defined this yet, but when we come to the examples, yeah, when we come to the examples of that kind, we will do that. So now your question is as follows. So you are now given this grammar, and you want to convert it into Chomsky normal form, but you want to use as few productions as possible. So the question is, how many minimum productions do you need in order to make this into the Chomsky normal form? So I'll maybe wait for a minute or two, and you can give this a try, and then we will discuss this. Okay, so let's discuss. So here you have, I'll just write the grammar as it is first of all. So you have x gives small x y gives capital X Z. What I will do is I'm going to add three more productions. So I'll add a gives small x, b gives small y, and c gives small z. So now all the three of these productions that I have written are of in the Chomsky normal form, because it allows you to have productions of the form where it only gives one terminal. Then what I'm going to do is I'm just going to replace um, each of the terminals into uh, into the into the productions that we have here. So this is what we have. Now let's see which of the following productions in the new grammar are in the CNF form already. So these three were already in the form, and now y is also in the form because it is written as product of two non-terminals. But s and x here are not in the form because they are product of three non-terminals. So what we will do is we will simply break them into smaller parts. So let's say s gives x followed by d, and d gives you y. So this is same as saying that s gives xt and d gives ya. So that is same as saying that x gives xya, which is what we originally had. So this is basically equivalent way of writing it. But now s and d both are in the CNF form. Similarly, you can do this for x. You can say x gives a followed by e, and e gives you ab. So again with the same idea, x gives ae and e gives ab. So this is as good as saying that x gives aab. So that is basically an equivalent way, and the rest of the productions remain the same. So you have a gives small x, capital B gives small y, and capital C gives small z. So the number of, and all of them are now in the CNF form. So how many productions do we have? We have 8 productions here, and you can show that you can see that there cannot be a small production. So each of the steps that we did were necessary to get the same grammar. If you try to come with a smaller grammar, you would end up missing some of the strings. So uh, therefore you basically, this is the minimum grammar, the minimum size grammar that you can generate. So the answer for this is B. So you need 8 productions. So if that is clear, we will take up this example. So yeah, so here you have this grammar, which is s gives a is b or epsilon. So notice that for the CNF form that we described, we said that you are allowed to give productions of the form that it is product of two non-terminals, or it could give you a terminal. So it does not even allow you epsilon productions. But if the language is generating epsilon, then if s is the start variable, then this kind of move is allowed. So if s is the start variable, then you can have epsilon transitions. But if um if um the the language does not have epsilon, then you are not allowed this kind of moves. So in this case, let's see which of there are two productions. One is s gives asp and s gives epsilon. So this is in the CNF form because s is the start variable itself here, so this is allowed. But s gives small a, capital S, the non-terminal a followed by terminal a followed by non-terminal b followed by terminal b, this is not in the CNF form because you're not allowed products of terminals and non-terminals. So this is not in the form. So our goal here is to bring this into the form. Okay, so I would just like to make one remark about, just to connect to the things that we did earlier. So in the last week we saw how to eliminate that is one thing we saw. And we also saw elimination of unit productions. So yeah, so basically what you do is, we say that if you are given a grammar G, you can always convert it into a CNF form G prime, such that the language of G is equal to the language of G prime. So this is possible. Now how do we do that? So notice that if s is if you have variable, some intermediate variable a, which somewhere gives epsilon, then we know how to use epsilon productions to eliminate this kind of variable. So if you apply step 1, then in step 1 you would have eliminated all the epsilon transitions. Now if you we also said that you are not allowed transitions of this form. You can't just have one non-terminal gives the other non-terminal. So in step 2 we can eliminate all the unit productions. Okay, so now what are the kind of productions that you can have? You can have a gives bc, this is fine by us. You can have a gives bcd, this is not okay. Or you can have a gives a set of uh, a long string of terminals, or you can have that they are kind of interspersed, so you can have a terminal followed by non-terminal, and so on. So this is what you can have. Now yeah, now our goal is that after doing the step 1 and step 2, these are the problematic situations that we can have, and in each of the cases we will see what can be done. So we will see this using example, so that it is more illustrative. So let's see, let's do the same thing. So we will identify which of the cases we are in, and we will apply the rules accordingly. So I'll get a new page for the okay. Okay, so I'll write the grammar here. Okay, so let's look at this example. So I'll take the first production, which is ASB, and I will add two more rules now. So I have capital A gives small a and capital B gives small b. So once this is added, I can rewrite this as S gives capital A, capital S, capital B, and capital A gives small a, capital B gives small b. So this is equivalent, because when I say S gives ASB, then we know that A has only one rule, which is A, and B has only one rule, which is B. So this is same as saying that S gives ASB, which is what we anyway had. So it's basically equivalent, just that we have written it as a product of non-terminals instead of terminals. Okay, so now what we want to do is, this is a product of 3 non-terminals instead of 1 non-terminal. So we will do the simple idea, which is break it into small parts. So we will say that S gives capital A small c, and capital A capital C, and C gives SB, and the rest of the productions remain the same. So what does this mean? Instead of S directly giving ASB, we have S gives AC, and C gives SB. This is same as saying that S gives ASB. This is exactly what we anyway had. So this is an equivalent way of writing the same, but the advantage is that now we have S as product of two non-terminals, C is product of two non-terminals, and therefore they are in the Chomsky normal form, and these are just giving one terminal. So now this is the grammar that is in the CNF form, and it identifies the same language. So just to finish this, we have S gives AC, C gives SB, and yeah, and A gives small a, B gives small b, and there is one more production that we are yet to write, which is S gives epsilon. This is what was there. This is what was there in the given example. So this is the final equivalent. I'm just highlighting it. So this is the equivalent grammar in CNF form. Okay, so we'll do okay, we will do the second part as well. So the second, sorry, yeah, the second question is almost similar. um, this is what you have, so maybe I'll just get this on the other page. Okay, so I've just gotten this grammar on the other page, and the question is same. Given this grammar, goal is to the goal is to convert this into CNF form. So what I'll do is, we will do the same thing. So we are going to write the same, we are going to write all the three productions separately. So you have S gives SS and S gives epsilon, and we will identify which of these are in the CNF form already. So if they are already in the CNF form, we will not touch them. If they are not, then we will try to change them. So here you have that S gives epsilon. This is already in the CNF form because S is the start symbol and you're allowed to have epsilon transitions. Then S gives SS. This is also in the CNF form because it is a product of two non-terminals. Then we look at this. So this is a product of a terminal, then there is a non-terminal, then there is a terminal. So this is not in the form and we want to change this. So yeah, so this is not in CNF form, so we are going to change this. So how do we do that? So we will follow the same idea for each of the the terminals. Here I'm going to have one symbol. Let's say A gives opening bracket and B gives the closing square bracket, and instead of writing terminals, I'm going to replace it with the non-terminal. So this is A S B, S gives SS, S gives epsilon, A gives opening bracket, and B gives the closing bracket. So this is equivalent to the earlier grammar, because when you say S gives ASB, A is nothing but the opening bracket and B is nothing but the closing bracket. So this is same as saying S gives opening bracket, S closing bracket. So it's the same thing but written differently. Now you just want to yeah, you are in a similar situation as earlier. Instead of product of uh, product of two non-terminals, we have a product of three non-terminals. So what we will do is we will break this further. So you have S gives AC and C gives SB and S gives SS, S gives epsilon, A gives opening bracket and B gives closing bracket. So it's the same idea that we saw earlier. So I'm not explaining this in detail, but finally if we write this whole thing all together, you have that S gives AC or SS or epsilon, C gives SB, and A gives opening bracket and B gives closing bracket. So this is the final grammar. So this is in the CNF form and it is equivalent to the grammar that we were given initially. So yeah, basically that is the whole idea. Now I want to yeah talk a little bit about some properties of the CNF. So let's take one example. Okay, so Yeah, so let's look at this. The question says that you are given a grammar G which is already in the Chomsky normal form, and you are asked that if you want to generate some string w which is in the language, and let's say length of w is n, then the claim is that you can derive it using 2n minus 1 steps in the past tree. So maybe I'll pause for a minute for you to think, and we will discuss this. So it is not very hard to prove this if we use the properties of the CNF form. So that is what we will do. But I'll maybe wait for a minute for you to think. Yeah. Okay, so let's discuss the solution. So okay, so yeah, so the claim is that if length of x is n, then number of steps uh, to derive x. So okay, maybe I'll use w just to be consistent. W is equal to 2n minus 1. So that is what we want to show. So what we will do is we will use what is called principle of induction. So we will use this by induction on length of w. Okay, so what do we mean by that? If so by induction, so okay, maybe let's look at the grammar. So you have some start symbol s, and it can give you a terminal, or it can give you something like this, which is product of variables. So if it is of the form that s gives a terminal directly, then you are just deriving a string of length 1, because you can't expand on this further. Once you get to a terminal, there is nothing to explore. So in that case, you are deriving a string whose length is 1. And how many steps did we need? We needed just one step, and therefore which is nothing but 2n minus 1, which is 2 times 1 minus 1, which is 1. So this is the base case. So base case is when length of w is equal to 1, then you only need 2 times length of 1 minus 1, which is 1 step for derivation. So this is going to be our base case. Now let's say let's look at the other case when s is a product of two non-terminals. So s is a followed by b. Now a is going to give us some string x, sorry, yeah, a is going to give us some string w1, and b is going to give us some string w2. And notice that length of w1 plus length of w2 is nothing but length of w, because w is nothing but w1 concatenated with w. So using that, we know the following observation, that uh, length of w1 plus length of w2 is nothing but length of w. Then if I look at okay, is it possible that the length of w1, can it be equal to 0? Is this possible? So we will use the properties of Chomsky normal form here. We said that s can give epsilon, this is allowed, but a cannot give epsilon, because because this epsilon transitions or epsilon productions are not allowed in A. So yeah, so this is not possible. Hence, we know that length of W1 is greater than 0. Similarly, length of W2 is greater than 0. And what does that mean? That basically means that length of W1 and length of W2, these are strictly less than n, because length of W is length of W1 is length of W minus length of W2. So this is strictly less than length of W, because W2 is at least is greater than 0. So that is why you have the following claims, and this is where we are going to invoke what is called our induction hypothesis. So what we say is that by induction hypothesis, what we have is that that there is number of steps required for derivation of W1 is equal to 2 times length of W1 minus 1, and number of steps this is equal to 2 times length of W2 minus 1. Now, how many steps do we need for derivation of W? So first thing is we use this production as gives AB, so that there we used one production. Then you use the number of steps required to derive W1 and number of steps required to derive W2. So this is number of steps for W1 plus number of steps for W2, and by induction hypothesis we know this is nothing but 1 plus 2 times length of W1 minus 1 plus 2 times length of W2 minus 1. So if we expand on this, we basically get this is nothing but 2 times length of W1 plus length of W2 minus 1 plus 1 minus 1. So this minus 1 and plus 1 cancel off, and this is nothing but 2 times length of W. Because of observation 1, we know that length of W1 plus length of W2 is length of W. So you have 2 times length of W minus 1, and this basically proves the induction. So yeah, so this was basically a simple argument that we showed using induction, and yeah, you had a simple base case here, and using the structure of the Chomsky normal form kind of made the argument very easy. So in a lot of cases, having grammar in this form helps you make lot of observe lot of properties about it, which can be useful. So yeah, so that is all about Chomsky normal form, and I think we may not get time to talk about the Gribag normal form, so that we'll take up later. But I had one more question, so about ambiguous grammar, so we'll take this up now. Okay, so I think I don't have the question here, so I'll go back to the previous. Okay, so yeah, so this is a question about ambiguous grammar. So in the last week we saw several examples about how to show that a grammar is ambiguous. This time we will see one example of converting it into an unambiguous grammar. So let us quickly recall what do we mean by ambiguous grammar. So you see that a grammar is ambiguous if there is some string x such that there are two different leftmost derivations for it that you can have in that grammar. So basically we mean that for the same string you have two different parse trees. If that happens for some string, then you say that the grammar is ambiguous. Now sometimes it is possible that you can take you have you have an ambiguous grammar and you can convert it into an unambiguous one, but sometimes it's not possible, meaning you cannot convert. No matter what grammar you write, it will end up being ambiguous. So such languages are called inherently ambiguous, and it's not possible to remove the ambiguity. So we will not look into examples of inherent ambiguous grammars, but we will do one where it is possible to convert it into an unambiguous one. So let's look at this example. So yeah, so this is something that you, this is a grammar. So we saw this earlier, that your all the programming languages that you have are essentially context free grammars. So this is some construct from a programming language. You might have seen this where you have nested if else, nested if then else. So here is a simplified version of the same code but written in the form of CFG. So you can pause, you can take some time to understand what is the language of this grammar. So I would recommend you do that, and once you know what the language is, we are going to do the question is to answer two things. One is that you want to show that G is ambiguous, and the other is that you want to show that you want to give a new grammar for it which is unambiguous. So I'll let you think. I really encourage you to pause and think for a while how to show that this grammar is ambiguous. So just recall that by definition we know you say it is ambiguous if there is some string which um, which can be derived in two different parse trees. So basically you want to come up with a string which has two different derivations possible. So I'll wait for some time. Yeah. Okay, so yeah, I'll go to the next sorry. um yeah, I'll start discussing the answer. So um okay, so this is the grammar that we have, and what we're going to do is I'm going to do a leftmost derivation for some string. So here you let's say you start with the statement which is your start variable. Then you have three choices: either you can take assign, or you can take if then, and then you can take if then else. These are the three variables. So let's say you take if then. So from statement we go to if then. Now let's look at if then. There is only one choice here, there's only one rule here, so that is what we will write. So here you have if condition then followed by statement. Now again we go back at statement, and statement has three choices: assign, if then, or if then else. So let's say this time we take if then else. So statement gives if then else, this is where we are. And if we look at if then else, then the production is just one rule. So we will just, there is no choice, we have to take that rule. So what is the rule? You have if condition then, there is some statement, else there is some statement. Now we have two variables, so that one is statement, the other is also statement. So which one should we expand first? The one which is in the leftmost, which is the leftmost variable, because we are doing leftmost derivation. So this is what we should expand first. And let's say this time statement gives assign. So statement gives assign, and assign has only one rule, so you have assign gives a equals 1. Similarly, we do the same for the remaining variable. So now statement is the only variable, and we do the same set of rules. Statement gives assign, and statement assign gives a equals 1. So this is the string that we end up generating. So the yellow part that is highlighted here is basically the set of terminals that we have. So what is the string generated? The string generated is if condition then a equals 1, else a equals 1. So that is the string that we have written here. Now what I want to claim is, I want to say that this string x that we have written over here has two different leftmost derivations. So one is what we saw here. Now I am going to show a different leftmost derivation for the same. So let us look at that. So I basically written the same grammar over here. This is the same grammar that is here for reference, so that we can see that how are the rules used. So statement is the start variable, and let's say this time instead of if then we take if then else. So this is the rule that we used. Then like we said earlier, if then else has only one production, so you get if condition then statement else some statement. Now this is the leftmost derivation, therefore we are going to expand on the leftmost variable, which is this one. So now statement, let's say out of the three choices, let's say it chooses if then. So this is what you have, statement gives if then. Now if then has only one production, so that's what we are going to write. So if then gives if condition then statement, and statement gives assign. So statement gives assign, and assign has only one choice, which is a gives 1. And similarly you do this here. So what is string generated by this? The yellow lines here basically tell you what are the non-terminals, and we're going to read it from left to right. So what is the string? String is if condition then a equals 1, else a equals 1. This is exactly the string that we had. We had if condition then a equals 1, else a equals 1. So there are two different leftmost derivations for the same string. So I've just copied the first grammar that we had here and the second grammar that we had here. So notice that we know that both are in the leftmost derivation form. We have two different pass trees that generate the same string, but they are different pass trees. How do we know that? You start with the same variable statement, but in the next step itself, here you have if then and here you have if then else. So these are different pass trees, but they still generate the same string. That's why this grammar is ambiguous, because for the string x there are two different derivations. So that basically does the sorry about that. So yeah, that basically does the part A, which is to show that the grammar is ambiguous. Now we want to convert it into an unambiguous grammar. So I just want to repeat this again. It may not be always possible to convert any ambiguous grammar into an ambiguous one, but in this case it so happens that we can convert it. So let's see how do we do that. So again, before you look into the solution, I would really encourage you to give it a try on your own, and see if you can do it on your own. So yeah, so like we've been doing today, we are, instead of getting one step answer, what we are doing is we are building the answer part by part, step by step, and then clubbing everything together. So that is what we will do again. So here you have the grammar, this is the original grammar that you are given, and our goal is to make it unambiguous. So let's do a natural attempt. So natural attempt is that the ambiguity kind of happened because there is a statement here and there is a statement here, and both of them can potentially give rise to the same constructs again. So we kind of want to block this statement from generating more and more things. So what we do is, let's do the simplest thing. Instead of allowing it to produce more statements, let's say it just does an assignment. So if you have if condition, then it just does some assignment. So this is our attempt 1. This is a small modification that we did. Instead of writing a statement, we wrote an assign. So let's see what happens now. So the string that we saw earlier, so this is the string that was causing the problem, that you had two different pass trees for it. Let's see what happens now. If you try to derive it using the same the same idea. Statement gives if then, but now if then just gives you if condition then assign, and this just gives a gives 1. So you were not able to assign, you were not able to generate that string using the first grammar. But let's see what happens with the second grammar. So you have statement gives if then else, and then you have just one choice for it, and if you try to expand this, then this only gives if condition then assign a equals 1. So this does not change anything, um, except that we just skipped over one step here. You can try, you can take your time and try this out, what happened to the second pass tree when we change the grammar. So you can show that now if you try to generate that string, there is only one way in which you can do it. So we have kind of removed ambiguity for that particular string. But is it possible that it is possible that maybe this is not the same grammar. So additionally, it is not enough to remove the ambiguity. It is, we also want to show that the new grammar that we got is generating the same language as earlier, so it should not be changing the grammar. So the step 2 is correctness part. So step 2 is that you want to show that the language that we generated is exactly same as what was there originally. So let's check what happens now. So this is the grammar, the step 1. This is the grammar from the attempt 1, where statement was just removed and replaced with assign. So let's look at this particular string. Okay, so let's look at this particular string and try to derive it. You start with statement, and yeah, and there is if condition then. So there is only one choice, you have to use if then. So that's what we did. And what does if then give? If then just gives you if condition then assign, and this just terminates at a equals 1. So you will not be able to derive this string y using g prime. So this particular string y is not in the language of g prime, but let's see whether it is there in the language of g. So let's check that. So this is the original grammar g that we had. So this is g that was given, and let's try to derive it. So here you have the statement that was that was the start variable, and let's say you take if then from if then you have only one choice, which is if condition then statement. Now there is one variable statement, and we want to expand on that. So let's say again you take if then, you follow the same step. If then gives if condition then followed by statement gives assign, and assign gives a equals 1. So this is the string we derived, if condition then a equals 1. So that is what y was. So it is possible to generate y in the grammar g, but it is not possible to generate it in the grammar g prime. So yeah, so the languages are not equal. So you have that L of g is not equal to L of g prime. Now what we want to do is, we want to be able to generate such kind of strings where there are if then, and there are lots of if thens followed by finally terminating in a equals 1. So how do we do that? It's just a simple modification that we do. So here we write this is the first change that we had made. Additionally, we are going to add one more production, which is if condition then if then. So now let's try to see whether it is able to generate the string y. So you go to statement, you go to if then this time you use the second newly added production. So it gives if condition then followed by if then, and now you use for this if then, you use the first production. So this gives if condition then assign, and assign simply gives a equals 1. So we could generate this string y this time with the modified grammar. So you can from this point, it's not very hard to see that this is indeed the same the equivalent grammar for the original one. So it generates the same language. So it is also unambiguous, like we saw earlier. So it is unambiguous and equivalent. Therefore this is the final grammar for the part B. So yeah, I think, yeah, so we saw some examples about CNF today, and next time next time we are going to look into some what is the Greybach normal form. We will look at PDAs, which is a new model I haven't described it yet, but we will look into what is a PDA. We will see some examples on this. And yeah, so I'll see you next week on Friday from 6 p.m. to 8 p.m. Okay, so I think, yeah, that is all for today. Thank you. Yeah. So I'll stop the recording.